In 1935, Albert Einstein, the very man who set the cosmic speed limit, found something in quantum mechanics that seemed to break his own laws. He called it spooky. For decades, the world's greatest minds thought he was just an old genius who couldn't accept the bizarre new reality. But here's the thing. They were wrong. The universe is spooky, and the proof would completely upend everything we thought we knew about space, time, and reality itself. So how did one man's nagging doubt lead to the most mind-bending discovery in physics? Let's get into it. So, is there a universal speed limit? Absolutely, and it's the speed of light. Now, this isn't just some arbitrary rule, it's the foundation of cause and effect. It's what stops reality from descending into chaos. Think about it this way. Newton's theory of gravity suggested that if the sun just vanished, we'd feel its gravitational pull disappear instantly. But Einstein realized that would create all sorts of paradoxes. For some people in the universe, the Earth would fly off into space before they even saw the sun disappear. So he fixed it. His theory of general relativity describes gravity as a ripple in space-time, a ripple that travels at, you guessed it, the speed of light. It takes a full 8 minutes to get here. This principle is called locality, and it's supposed to be non-negotiable. And this is what led Einstein to utter his famous phrase, spooky action at a distance. For him, this wasn't just some quirky little feature of a new theory. No, it was a ghost in the machine. It implied that two particles, separated by light years, could somehow communicate in an instant, smashing the cosmic speed limit he'd worked so hard to establish. To him, this was a full-on assault on the fabric of reality, and he was absolutely convinced it meant the quantum theory had a huge piece missing. Okay, so before we can really dig into the paradox, we have to appreciate the very law it seems to violate, a law that Einstein himself wrote. So, what exactly was this problem that had him so bothered? Well, back in 1927, Einstein came up with a thought experiment. Imagine you fire a single electron. Quantum mechanics tells us its location isn't a single point, but a wave of probability, kind of like a cloud of maybes. It could be here, or maybe over there, or way over there. But the second that electron hits a screen and you measure it, you find it at one specific spot. And that entire cloud of maybes all across the universe vanishes. Instantly. A measurement right here has an immediate effect everywhere else. And for Einstein, that was a blatant violation of his speed limit. Einstein wasn't about to let this go, so in 1935, he doubled down. He got together with Boris Podolsky and Nathan Rosen to publish the now famous EPR paper. They sharpened his argument, and in doing so, they introduced the concept that would become the absolute heart of this mystery, quantum entanglement. Okay, so what in the world is entanglement? Here's a simple way to think about it. Imagine you have a pair of gloves. You put one in a box and mail it to the other side of the planet, and you keep the other box. You have no idea which is which. The very instant you open your box and see a left-handed glove, you know, with absolute 100% certainty, that the other box contains a right-handed glove. Quantum entanglement is the subatomic version of that, but way, way weirder. Say a high-energy particle decays into two new particles. Their properties, like spin, become linked. If one is spin up, the other has to be spin down. They behave as a single, connected system, no matter how much space you put between them. And this is where the paradox really shines. Let's say you separate these two entangled particles by light years. Then you measure one of them and find its spin is up. At that exact same moment, you know that its partner, maybe in a whole other galaxy, has a spin of down. So how did that second particle know what result to show? It really seems like some kind of information, some signal, traveled between them faster than light. This discovery kicked off one of the greatest intellectual battles in the history of science. You had Albert Einstein, the man who believed reality had to be local, predictable, and sensible, and in the other corner, Niels Bohr, one of the fathers of quantum mechanics, who basically argued that the quantum world is just fundamentally weird and we just have to learn to live with it. So it really all came down to two competing explanations. Einstein's view was that the particles must have some kind of predetermined hidden variables. Think of them like secret instructions written down the moment they were created that tell them what spin to have. It's a perfectly local, common-sense explanation. But Bohr? He said, nope, there are no hidden instructions. The particles are in a totally undefined state until you measure one of them, which causes the whole system to collapse instantly, no matter how far apart they are. He was arguing for a fundamentally non-local reality. And here was the real kicker. For decades, you couldn't prove who was right. Both Einstein's local hidden instructions theory and Bohr's non-local spooky connection theory predicted the exact same results in every experiment you could think of. With no way to test it, the physics world just kind of sided with Bohr, wrote off Einstein's concerns as old-fashioned philosophy and got back to work. The debate was essentially dead until a physicist digging through old papers found a way to set a trap for reality itself. Yeah, for decades, this was just a philosophical stalemate. But then, in the 1960s, a physicist named John Bell, who always felt like Einstein's objections were swept under the rug too quickly, stumbled across that old EPR paper. He became obsessed. He wondered, was there a way to force the universe to show its hand? A way to turn this philosophical argument into a real, concrete experiment? Bell's idea was just pure genius. Remember our gloves? If you and your friend both agree to check for left or right, your results will always be perfectly opposite. That's what both theories predicted. But Bell asked a clever question. What if you measure from different angles? What if you check for, say, palm up or down, while your friend checks for thumb left or right? Suddenly, Einstein's secret instructions theory and Bohr's spooky connection theory actually predict different statistical outcomes. Bell had found a question that the universe couldn't dodge. Bell's math laid it all out with incredible clarity. If reality is local and based on hidden instructions, like Einstein believed, then when you measure at these different angles, the results should disagree more than a third of the time, at least 33%. But if reality is non-local and spooky, the disagreement rate would be exactly 25%. The argument was no longer about philosophy, it was about a number. So the stage was set for the ultimate test. Through the 1970s and 80s, physicists like Alain Aspect finally built the experiments to actually perform Bell's test. They created pairs of entangled particles, fired them off in opposite directions, and measured them at different random angles over and over and over, collecting the data that would finally settle this epic debate once and for all. And the result? Every single time the experiment has been run with more and more precision over the years, the universe has given back a clear, shocking, and unambiguous answer. The disagreement rate is 25%, exactly as quantum mechanics predicted. The conclusion is just inescapable, and honestly, it's one of the most profound discoveries in the history of science. Reality is non-local. Einstein was right to be worried, but he was wrong about the reason. That spooky action at a distance he was so afraid of isn't a flaw in the theory, it's a fundamental feature of the universe we live in. But wait a minute, does this mean we can build a faster-than-light telephone and break causality? Well, no, and the reason why is just beautiful. While the correlation between the particles is instantaneous, the outcome of any single measurement is completely and utterly random. You can't force your particle to be spin up to send a 1 or spin down to send a 0. You can't encode a message. The universe allows for this spooky influence, but it cleverly protects cause and effects by cloaking it in pure chance. So this forces us into a very strange corner. We either have to accept that we live in a non-local universe where spooky action is just a fact of life, or we could consider an alternative that might be even stranger. The many worlds interpretation of quantum mechanics says that when you measure a particle's spin, you don't force it to choose. Instead, the entire universe splits in two. In one universe, you measure up. In a brand new parallel universe, a copy of you measures down. Both things happen. Now, this idea is completely wild, but it has one huge thing going for it. It saves locality. There's no spooky connection, just an endlessly branching reality. So that's the question we're left with. Do we live in a single universe tied together by invisible, faster-than-light threads, or do we live in an infinite ocean of parallel worlds? The verdict on that is still very much out.